Okay. So the simplest one is I plus 1. And by the way, these will be implicit. And I'll tell you what implicit is just in a bit. So yi plus 1 is yi plus delta x fi plus 1. So this is Adam Moulton order 1, or Adam's first closed formula. So take a look at that equation. So the one which I've marked in red, it looks very similar to the Euler's method, where yi plus 1 is yi plus delta x times f. But the big difference being that it actually requires the value at I plus 1, not at I. This is what we used for Euler's. This is what we're using for this multi-step method. The thing about this method is that the value at I plus 1 is not available to you. You only know about the system at time I or before I, but you do not know what happens after I. And so what will happen is that part is actually unknown. Usually when you solve this with single step method, everything on the right is known, but everything on the right is not known. In fact, I plus 1 is not known. To illustrate this further, let's just take an example. So here's an example. If f of I is yi square, you'll have yi plus 1 equals yi plus delta x, f of I plus 1, so it'll be yi plus 1 square. Okay, so this value is not available to you because it's asking for the value of y at the next time. But what you could do is you could move things around. You could move this yi plus 1 on the other side, and you'll get I plus 1 minus yi plus 1 square equals, sorry, I should put delta x yi plus 1 square equals yi. And then if you write it like this, minus yi equals 0. I just moved the y on the other side. This thing here is a quadratic equation in yi plus 1. Okay, so this quadratic equation has to be solved. Now, quadratic equation is easy to solve. We know the solution to this. But if this was more complicated than yi plus 1 square, it turns out that you cannot solve this with like a simple formula. You'll have to use root finding. So many times you'll have to actually do a root finding on top of this. Every step you might have to do a root finding in order to solve for this. So one way of solving this is if you know something special about that equation, like this is a quadratic equation, you can solve it. But the other way it could work out is that you just have to use root finding. So another example, if you really want to see how root finding will come in place, if you take f of I is e raised to yi, then yi plus 1 will be yi plus delta x e raised to yi plus 1. And now you have yi plus 1. I'm going to move this on the other side. Minus yi equals 0. This is, by the way, known. These two are unknown. So now you need to do, if you take this equation, it will be something like this. F of yi plus 1 equal to 0. And then you'll have to use do some kind of root finding. Example, Newton-Raphson. So use Newton-Raphson, solve for yi plus 1, and then you can proceed. So it is much more complicated, right, than doing what we had explicit formulas. So this is why it is known as an implicit method. An implicit method will have some kind of a nonlinear equation showing up, and solving that nonlinear equation is a problem by itself, right? It's a hard thing. But these methods, turns out that by doing it this way, they actually are much more stable than they are with explicit formula. You can actually go for a very big time step, delta x, uh, with an implicit method than you can do with a explicit method like Euler's method. Okay, so now I will give you various formulas for this. Let me just write the formula for I for the second order. So yi plus 1 is yi plus delta x f of I divided by 2 plus f of I plus 1 divided by 2 plus order delta x cube. This is Adam's second closed formula, or Adam Moulton second order formula. So let's talk about a generalized Adam Moulton formula. It'll have this form: yi plus 1 is yi plus delta x summation m goes from 0 to n minus 1 beta, it's called that beta star, nm f of I plus 1 minus m plus the truncation error, it is of the order of delta x n plus 1. Okay, so this is a handy formula. And then this is what you want to use if you are told any order. And then accompanying this is a table. You put in the table there. Okay, so this is basically giving you values for this beta. It's right here. And you can check the value for the first one, the second one. So we have essentially 2, 1, and 1. That's the second formula over here. Okay, so the next step is to apply this. Let's apply it to the same problem we did, but using Adam Moulton's method. So the problem is the same. Copy. The only thing I'm going to change is tell you to apply it with the Adam Moulton method of order 2. Okay, so again, what you'll see is that you cannot apply this. So if you look at, well, let's just write the formula first. I plus 1 equals yi plus delta x f of I divided by 2 f of I plus 1 divided by 2. What we observe is that we have I plus 1 here. So if you put I equals 0, so we'll write y1 equals y0 plus delta x f0 plus f1. So it works fine. There's no problem in applying it for I equals 0. So there is no self-starting problem with this particular set of methods because it doesn't require value in the past, negative values, but it requires future values. So it's no problem. So what we'll do in this case, it makes it much easier, is to actually develop a general formula for yi plus 1 and then use it. It becomes very easy to do it. In this case, I chose the problem such that you can actually solve for yi plus 1 easily. You don't really need root finding. So let's put in the values here and see what we get. I plus 1 equals yi plus delta x. Fi, let's just pull this 2 out. So Fi is xi minus yi plus xi plus 1 minus yi plus 1. Okay, let's move things around. In fact, what I'm trying to do is I'm trying to take this yi plus 1, whose value I don't know, and trying to club those two together. So here's 1 from here, and then this is going to be delta x divided by 2 with a minus sign, so it'll be plus delta x divided by 2. And then whatever remains here, you can put it all together. So delta x, let's see. So yi, this yi, so yi 1 minus delta x divided by 2. So I just took this part, and this part, combine it together, and then plus delta x xi plus 1 divided by 2. So our formula is yi plus 1 equals yi 1 minus delta x divided by 2 plus delta x xi plus 1 divided by 2 divided by 1 plus delta x by 2. So all we have to do now is use this formula. We actually develop a closed form solution, which happens only special cases. Like, this is a particular example where you can develop the formula, but in general, you cannot get a formula like this. So now we can apply the formula. What I'll do is I'll put I equals 0, so I can get the solution for y1. Move this to the next page. Yeah, so let's look over this and write down a formula for y1. Put I equals 0. y1 equals y0, 1 minus delta x divided by 2 plus delta x x0 plus x1 divided by 2 divided by 1 plus delta x divided by 2. So we know that at x0, y0 is 1. The step size is 0.1. 0.1 again for the step size. X0 is 0. X1 is 0.1 divided by 2 divided by 1 plus 0.1 divided by 2. So everything is known. So we get on the right hand side, so 0.9095. And you could do this for I equals 1, 2. So y2 equal to y1, 1 minus delta x divided by 2 plus delta x x1 plus x2 divided by 2, the whole thing divided by 1 plus delta x divided by 2. So y2 will be y1, which is 0.9095, 1 minus 0.5 divided by 2 plus 0.5, 0.1, 0.2 divided by 2, the whole thing divided by 1 plus 0.1 divided by 2. Okay, let's just take this to the new page. Okay, so again, everything on the right side is known. So we can compute y2. It is comes out to be 0.8372. So what I'm going to do is I'm going to give you a table, and you should do the calculations beyond the ones I did here in class. We have 0, 0.1, 0.2, 0.3, 0.4. Okay, and in particular, if you want to check the values which you want to report are these values. These are the ones which we're interested in. This is the solution. Okay, so beyond the two I computed, just check the value. So good thing is self-starting, but could be cumbersome to solve at each time step, because you might need to use you may not be able to do this with a calculator. You might have to use Newton-Raphson, which means programming.